Hi there, guys. So I'm going to go through the example questions before 8E. But just before I do that, I'm going to talk about the other way of writing down complex numbers. So you have a Cartesian or a rectangular form. And so on your calculators, you will normally have the mode set to rectangular form. And you also have polar form as well. And so polar form comes from this diagram here. And for that, you also need to know about the modulus of your complex number and also the argument of your complex number as well. So we'll talk about those things before going into the two example questions. Okay, so this bit before 8E, this is an important box here. So we've still got the complex number z equals a plus bi represented on the Argand diagram here. So Argand diagram where we have the real axis, the imaginary axis, and we have a across and b times by I up, if you like. So b lots of the imaginary amount upwards. And so we can plot that point z here. So that's where it is. So that's just coming from, putting a coordinate point there, A, B. Apart from it's not a coordinate point here, it's instead just Z, which is A plus B I. Okay, so there we go. That's the place on the Argand diagram. And you can see that we have here the length of this vector is r. Now you can find that just by doing Pythagoras. So do a squared plus b squared and take the square root of that, and that will be r. And then we have the argument of the complex number here as well. And the argument is just the angle as measured anti-clockwise from the real axis, from the positive real axis. So a bit like how we set up our cast diagram, if you like. So we're always measuring from the x-axis as your y-axis, and that's how we get out a lot of trigonometry. So we start talking about angles here measured from the x-axis. Okay, or if you like, our unit circle, you might know it as. Okay, so we can obviously use the r here and the theta in this right angle triangle to work out the adjacent length, so the length which is next to theta, by using the cosine triangle, of course. So CAH, and we can see that the A, if you like, are adjacent, just happens to be called A as well, or begins with A as a coincidence. If we want A, we're going to do cos times by cos of theta, or cos of the argument, times by the hypotenuse, and that's exactly what we're getting here. Okay, and likewise, you can do the same thing, of course, to find the opposite length using sine. Okay, now what you should know is that Z, not only A plus the I, that's the rectangular form, but the polar form of this would be r cos theta plus, in this distance, plus this, plus r sine theta I. Okay, now that can be factorized in this version here, and from this factorization here, the cos theta plus I sine theta, because we write it so often, you can just write that as r cis theta there. So this is just an abbreviation here, where we're really saying we've got cos plus I sine theta. So they've just taken the I to the front there. Okay, so that's where this comes from. It's the abbreviation of cos plus I sine theta. Cos theta plus I sine theta. We've just factorized out the r. So this gets written a lot. It's not a mistake. They've not typed in cos. The I shouldn't be an O. This actually stands for cos theta plus I sine theta. Okay, right. So this is your polar form, and this is your rectangular or Cartesian form. Cartesian coming from Cartesian form. So we've got cart in the middle there, and that's coming from Descartes, the famous mathematician and philosopher. Okay, so let's have a look at the questions then. Now, a lot of these questions you can do on your calculator, of course, but it's useful to be able to put them on diagrams too. So let's look at example 7. And they're not giving you a calculator option in this one. So let's do this one by hand. So this one's saying there's Z1, Z2, Z3. It says calculate the modulus of Z1. The modulus of Z1 is just talking about the length of that vector. So if we put it on here, we'll see that that's 2 across on the real axis, and on the imaginary axis, that's 2 up. So we've got this point here, that's Z1. Okay, so we want here the the length of that one. Clearly, that's just going to be a I. It's going to be 2 squared plus 2 squared, all square root, which is obviously giving you the square root of 8. Or you might want to write that as 2 square root of 2. Now I'm going to go directly on to working out the argument of that complex number there. So the argument is going to be this theta here. And in fact, you can see quite easily that that's going to be 45 degrees. You can obviously work that out using, if you like, tan, or you could work out the length of this using cos or sine. It doesn't really matter because you have the length here, of course, as well. But obviously, using tan would be the more obvious option there. Do 2 divided by 2 and do inverse tan of that. So you could do that if you wanted to. Inverse tan of opposite over adjacent. But that's 45 degrees. It asks for our answers in radians. So, of course, in radians, pi is equal to 180. Pi over 2 is 90. Pi over 4 is 45 degrees. Now, you can do all of the other ones in similar ways, so I'm not going to spend my time doing these things here. But, you know, bear in mind that when you get to something else like this, let's say, actually, let's go into this one here. We've got 3 plus 4i. So 3 and then the 4i there. So when we work out the angle for this one, you know, what you might want to do is work out this angle and take it away from 2 pi. So 2 pi is going to be all the way around, and we can take this off to get just this amount around from the positive x direction, or real direction, if you like, in this case. So there's real, there's imaginary again, and this is the angle which we need to measure. So you might want to work out this one using tan, so tan to the minus 1 of 4 divided by 3, and then take that off 2 pi. Make sure, of course, that your calculator is in radians. Okay, now in the next example, we'll see how to do this using our calculator as well, but at the moment we're just doing it using written methods. So for part C, it says find the area of the triangle with these vertices. Now, what it's asking us to do there is work out the area of the triangle on the Argand diagram. So on the Argand diagram, and we could equivalently do this, instead of using the Argand diagram, we could use just a normal coordinate system. It would also work for us here. But we're talking about these 3 positions here. So we've got 2, 2, so that's Z1. We've got 2 there, and 2 there, and we've got 3, 4. So we've got 3 and minus 4 there. So that's going to be this point down here, and then we've got minus root 3. So that's somewhere between 1 and 2. So that's over here. That's minus root 3. And we've got 1i there as well. So that's going to be up here. So that's going to be our Z3. That was our Z2. So what they're asking here really is saying, well, what's the size of this triangle here? And it's not going to matter if you do that on a regular coordinate grid or on the Argand diagram, in fact. Okay, now in order to do this, we've already worked out this length, and this length here, and we've worked out this angle, and this angle, and this angle here. So from that information, from the sizes of those lengths there, and from the arguments which we found there as well, we should be able to use a half AB sine theta to work out each of the areas of this triangle. Let's just put all three of them, and this one, and then this one here. Okay, so each of those triangles we should be able to work out by doing, of course, this length times this length halved, and then times by the angle in between. Now the angle in between is going to require you to make some calculations. Of course, if you want this angle here, you'll need to do the angle, the argument for Z3, take away the argument for Z1. So they're not too difficult to find out, to be honest. Okay, and that's the way in which the book deals with it, and I would really recommend that you make a neat diagram in this case in order to answer that question. You can do things differently here. You could potentially just come up with a rectangle around here. Okay, and you can see that that rectangle has a length here of 3 plus the square root of 3. That's just the difference between these two here. And it has a height of, that's 4 and that's 2, so it has a height of 6, that's minus 4, sorry. So we can work out the total area there, and we can take off this and this and this area, and that would be another equivalent way of doing this question as well. And you could deal with that just on a regular coordinate system there. Okay, so let's have a look at their answers that they're getting from the book for this one. So on the next page, so they've done it in the way in which they're saying, well, let's split it into 3 triangles going into the center, into the origin here, as to the first explanation there. And obviously there's a lot of working out to do, and you're getting the total area of 11.7. Okay. So the area here doesn't require you to have eyes. It doesn't come out as a complex answer in this case. It's just what's the total area it's covering. Imagine that this is essentially an XY coordinate grid. Okay, so there's that. And now let's look at example 8. And then we're into the exercise. So on example 8, this one here, you can see that this one's got a calculator option. And the calculator option is really useful. If you click on it, you get this thing here. Now, there's things to say about this as well. So the question starts by saying, write the complex number in modulus argument form. So modulus argument form. So what are they requiring us to do there? So they want, what's the modulus, what's the argument, and put it in polar form. So it's kind of strange that they're calling it modulus argument, but they basically want you to come up with the polar form. Now you will notice that when they do this on the PDF here, when they show you how to do this on the Ti-nspire, you will notice that in fact they will tell you to type in 2 plus 3i. They say I is pretty easy to select. You go to the pi key, so you don't go to the keypad, the keyboard at the bottom. And then it says if you go to menu and then number and then complex number tools and then convert to polar form and then press enter, it gives you this strange thing here. So it gives you e to the power of 0.983i times by 3.61. And that's saying that's equal to 3.61 cis 0.983. So that's really strange that they're giving it to you like that. Let's just copy that one. Okay, so it's giving this thing here. And your calculator will give you this. It will not give you this. And this is in fact yet another form. And this is called Euler's form. So it's putting complex numbers in terms of exponentials here. And this is another use for the number e in mathematics. But this is equivalent to this. Now you need to recognize that so that this part here is your angle. So this is theta I, if you like. This bit is theta, and this bit here is your r. So you need to recognize that in order to write it like this yourself. Okay, so when it puts it in polar form, it not only puts it, it doesn't put it in this argument, the modulus argument form, which is kind of what they're asking for. It puts it in a different polar form, which is Euler's polar form. Okay, so you need to recognize that this power is your theta, and this is your modulus. This is the size of the complex number which we have, and then you will create this thing here. Okay, so also you can go in the other direction as well. So if you typed in, if your calculator mode was on the rectangular mode, then you can put in a complex number in polar form by using brackets here, what they're calling parentheses, and they're saying if you put this in brackets, if for example you say we want to put in 3 cis 0.4, so that's your polar form. So we would put in 3 as the length of the vector, sorry, not the vector, the complex number. So put 3 as the size of the complex number in brackets, and then you need to go to control, and then there's a little key to the right hand side. Your calculator will give you this kind of book option, and there's loads of functions and different things which you can select in there. And then if you go to this infinity and beta with a degree symbol in, if you click on that, which I think is in the third section in there, so you might need to use your keypad, your pad to move across to this. So then you can select this angle symbol, and then you put your angle in as 0.4 there. And of course, make sure that you're set up in radians. Now, if you do that and you press enter, then again, you'll be given your complex number in this form down here. So you'll be given rectangular form because your calculator is set up in rectangular form. Okay, so that's worth experimenting with. That's going to save time in exams. But again, let's go back to the question and see what we can do in a written method. So let's just copy this one across again. So it says write the complex number 2 plus 3i in modulus argument form. Now, again, I would probably just do that's 2 across, that's 3 up. And I would work out the angle here using tan. So that would be using tan minus 1 of 3 over 2 would give us theta. And the modulus, so that's the argument that we found there, the modulus there is just going to be equal to r, which is square of 2, square of 3, all square root. And that's going to give you, so that 9 plus 4, so that's the square root of 13 now, okay? Right, and so for part B, it's saying find the form a plus bi, the complex numbers with the following modulus and argument values. Now, again, this is easier to do on your calculator. Again, you can set this one up as 3 angle 4 using that book function. So that's control and infinity beta, or I think actually you can go directly into the book function and find that. So you can just do that, and that will give you what you need. However, you could potentially do it using a written method as well. So in this case, we could draw this one out. We could say, well, that's, I know that's 3 there, and this is 0.4 here. And so we could use sine and cosine to work out the opposite length here, to work out the opposite length. So, you know, you're going to get SOH. So the opposite is equal to your imaginary part. So that will be sine of 0.4 multiplied by 3. That will give you your imaginary part. So we could put the I here, and then we could say that's also plus 3 cos 0.4 as well. So this would also work too. That's a perfectly fine way of doing this question too, without resorting to using your calculator. Okay, now with this one here, I would draw a diagram out. I would just try and think, well, where is 3.4? Well, 3.4 is beyond 2 pi, so that means we're coming full circle and a little bit more. So we need to figure out which quadrant we're in for this in order to think about our triangles here as well. So we can see here we've got, so take away 2 pi, so this is going to be 3.4 take away 2 pi. I'm wrong, sorry, I'm wrong. Sorry, that's 1 pi, isn't it? 2 pi is 6.28, sorry. 3.4 is just beyond here. Okay, so it's just beyond, so this is 3.4 take away pi, and that's going to give you this angle here. Now that's the angle which is necessary if you're going to then say, okay, look, there's your 5, and here's your right angle triangle, and that's our minus there. And then we're going to work out, again, the opposite length. Again, we can do sine of this, and that will give us our opposite length, and also we can do cosine of this times by 5, and that will give us this length here. And then, of course, we'll need to make this one negative. Now, of course, you can actually do that by simply typing that straight in. It will still work, of course, if you do cos of 3.4 plus 5i sine of 3.4. But the sine of 3.4 is going to give you that negative height straight away. Okay, so I'm making a bit of a meal of that one, in fact, but I'm trying to give you some sense as to where this is and how to do it by sort of thinking it through as well. Okay, but the formula is still going to work in that case for this part here. Okay, guys, well, hopefully that's useful. And yeah, you can see the way they've done that. You can see they've done that without going to the calculator, in fact. Okay, so 8E comes next, and 8E only has 4 questions, so make sure you get maximum practice there. And now next time around, we're actually going to do a bit more with this Euler's form and do a bit of working out with Euler's form. And then beyond that, so for myself as well, we're going to do powers of complex numbers, so we get 8F, and I think there's one more after that, which I think is 8G. So 8G is then done. Okay, so 2 more exercises after this one, and we are done with complex numbers. Okay, guys, thank you very much, and good luck with the exercise.